So in this series, we're going to talk about how to measure photocurrent of different materials. So we're going to start this video off with just measuring N-type silicon. And then we're going to move on to different materials. So in the next videos, we're going to look at photodiodes and more sophisticated devices. But even within N-type silicon, we can have things like non-ohmic contact, so ohmic contact, different types of, different levels of doping, and so on and so forth. But we're just going to constrain our discussion today with lightly doped or moderately doped silicon. So let's quickly draw out our silicon wafer here. So let's just say we have a chunk of silicon. So this is N-type silicon, and what we're going to do, or what that means is we have a whole lot more, a whole lot of electrons in this system. So, and we also have our holes, right? Much fewer holes, which are the minority carriers, and the electrons are majority carriers. So what happens when we connect this piece of silicon to some bias, let's say 1 volt, and obviously this is completing the circuit, and we have some kind of load on the circuit, which we're going to use to measure our current. So when we apply this voltage of plus 1 volt, what happens is the electrons are going to come rushing in to this bias, or to the positive terminal, and they're going to create a current, and the current flow is going to be in that direction, opposite to the electron flow. So let's say, for the sake of simplicity, when we're biasing it with 1 volt, what we get is 3 electrons that pass through the circuit. So we know from Ohm's law, if we bias it to 2 volts, what we're going to have is 6 electrons, and so on and so forth. So what is this going to look like in an IV curve, or a current versus voltage curve? So this is not going to be up to scale, but you can kind of tell that it's going to be something like, it's going to be something like 1, 2, and this is going to be 3, 6, and you can get an idea that it's supposed to pass through these two, so something like that. It's going to be a straight line across if we're making ohmic contact. We're going to talk about this in a little bit, but just assume that it means perfect contact with whatever our copper piece is that we're using as terminals or electrodes. So that is what we expect. So this would be the case, let's call this case 1, where we're in the dark. So absolutely no external sources that might increase this current. So I'll talk about that, or give us photocurrent. So actually, let's talk about that now. So case 2 would be when we have light shining on it. So when we have light shining on this material, what's going to happen is let's draw out our piece of silicon again, but let's make it much bigger this time, just so you can see. So again, we're just going to assume we have the same number of the same level of dopants. It's not going to be to scale, but say you have the same level of dopants and connect the circuit in the same exact way. 1 volt here, and yeah, plus 1 volt here. And so what happens, the difference between the other time and or case 1 and case 2 is that we're shining light on this. So you are shining light of certain energy onto your piece of silicon. So what this does is it's going to create an electron-hole pairs. So a hole and an electron. So it's going to create an electron-hole pair. Let's say we're creating 2 very energetic light, and you have 2 electrons, and 2 holes created. So if 1 electron is created, you have a hole. But yeah, what happens now is, instead of when you're applying 1 volt, you're getting 3 electrons here. When you're applying 1 volt here, you're going to get 3 electrons that we had before and 1 more electron that's photogenerated. So essentially what exciting with with light is doing is that it's creating more electron hole pairs in the system, which can obviously go and contribute to the current. So that's the rest of our circuit, and again the current flow is going to be in that direction. So you can see that if we have plus 2 voltage, you might be able to say there's 1, 2, 3, 4, 5, 6, 7. Sorry. So you can say we're going to have 8 electrons created. And for the sake of simplicity, I'm just going to say these are the 2 photogenerator electrons. That doesn't necessarily have to be all the electrons are. Like, the system doesn't know which ones are photogenerated or not. But in this case. So yeah, what does our IV curve look like? So our IV curve is going to look something like 1, 2, it's going to be 4 and 8. So you can see it's going to be something like that. And compared to the previous one, it'll be 30 and 6. So, sorry. So in the previous case, what we're going to have is an IV curve of something like that. So this is dark and this is light. So here we're making the assumption that this is energy much greater than the band gap of silicon. So it needs to be greater than silicon in order to generate electron hole pairs. So you might say, let's end the video here. Why? We're just gonna, our photocurrent is gonna be, or rather, our photocurrent is gonna be the current in case 1 or case 2 of light minus case 1 of dark. So why don't we just do that? And let's say at 1 volt, we're just gonna have 4 minus 3, and you're just gonna say, let's say it's 1 amps. You're like, that's it. Will this work? But in reality, and ideally, yes, but in reality, no. And why that is this difference is the difference between the light and the dark is very, very small. So instead of 1 amps, instead of 4 and 3 amps, it's probably going to be 4 and 3.9999. Not exactly like this, but something like that. So I'm exaggerating to show the idea, but it's going to be something like that. So how can we solve this problem? Obviously, there's going to be a lot of system noise, so it's going to be very, very hard to differentiate between what is due to the photons and what is not. So that's where our lock-in amplifier comes in. So what we're going to do is we're going to modulate the light that is shining on, meaning we're going to have, say, one pulse every 1 second. So we're going to have a 1 hertz frequency for the light. And so what that means is, let's make a plot of time versus current that's generated. And for the light, for the case where the light is on, let's say this is at 1 volt bias. So when the light is on, we're going to have 4 amps, and when the light is off, we're going to have 3 amps is what we said. So let's see, 3 amps. So initially in case 1, we're just going to have 3 amps across whatever time scale. And in case 2, similarly, we're going to have 4 amps across whatever time scale. Again, this is the exaggerated version. So the difference is not actually going to be 1 amp, it's going to be much, much smaller. But for the case of explaining this, let's just say it's 1. And let's say this is 1 second, this is 2 seconds, 3 seconds, 4 seconds, and so on. So, and I'll move this here just to align with the grid. So what you might say, what we might do when we modulate this light like that is, initially it's going to be on, and every half a second it's going to switch to 3 amps. And then we're going to have, because remember our frequency is 1 hertz, so we're going to go in 1.5 seconds, we switch, and so on. So we're going to have this switching pattern. So in reality, again, it's not going to be this huge. It's more so going to look like this. So you might have like 3,000 here, and over here the current might be, again, like all these values are exaggerated, but 2,999, something like this. So it's very, very hard to actually, like, given the system, it's going to be very hard to actually tell apart when we have light or when we have dark, when we're in the dark. So how we achieve this is using a lock-in amplifier. So what a lock-in amplifier does is it's going to have so this is our signal wave. So signal wave. And what a lock-in amplifier does is it adds a reference wave of the same frequency. So we tell it the frequency. And this reference frequency is going to have a much larger amplitude, and so on. It's going to have a much larger amplitude, but the same frequency as the modulated light. So remember, you said 1 hertz frequency. So it's still going to be 1 hertz, but it's going to be much, much, much more exaggerated. So I won't go into the details of how the signal and the reference are mixed, but maybe in the future we'll go into the details. But for now, what I want you to know is these two are mixed such that everything on this frequency is more, this frequency, the signal from this frequency, so is amplified. So essentially it amplifies it, and we're going to have a new signal, an updated signal with the same frequency, but much lower noise, or like you can resolve the signal better. So initially what we were measuring was this, and we weren't sure, what we were measuring was this, and we were very unsure of what the actual photocurrent was, because it's hard to subtract these two. But now it really tells us, after we do our calculation and adjustment, it's going to tell us that this is 2,999, this is 3,000, and now you can like easily subtract the two because you can see the difference. One very important thing to note is a lock-in amplifier is used with a low-pass filter, and what that has to do is, let's say that's your frequency in hertz. So, or to simplify this, so amplitude. So what a lock-in amplifier does after it mixes it is it's going to have a signal at the subtraction of the two waves, the frequency of the two waves, and at twice the frequency. So what a low-pass filter does is it actually filters out. That's how a low-pass filter is represented. So it actually filters out this 2 omega, like the signal at 2 omega, because we don't really need that. And at the same time, what it does is it also like filters out other signals above this range, kind of like two birds, one stone kind of thing. It filters out these higher frequencies in the same process, increasing the signal to noise ratio at the same time. So good things. So this is the low pass filter. It's very important. So now let's go back to our 3 and 4 amp example. So finally, what we're going to do here is we're actually going to determine the photocurrent. So we did all this, let's actually determine the photocurrent. So let's say we have 1, 2, 3, 4 volts, and let's say 2, 4, 6 amps. And similarly, we're going to have -1 here, -2, -4, -6. Sorry, -6 amps. So, so in case 1, I think I was using green for case 1. So in case 1, what we have was at 1 volt, we had 4 amps. So, and 2 volts, we had 8 amps. So, and similarly, we had 4 amps, and at 2 volts, we had 8 amps. So you can kind of see the IV curve was like that. And in the second case, so this is, or the first, this is the second case, this is with the light on, and with the dark case, what we had was 3, 6, -3, -6. So that was our situation. So now we can actually subtract out now that we know what the actual value of the light and what the actual value of the dark is, and we have a good signal to noise ratio, what we can do is we're going to have the photocurrent at, let's say, 1 volt is equal to the light, I light, minus I dark, and that will be 1 amps. And similarly, at 2 volts, it's going to be 2 amps. You don't, like, you see that they're following a straight line. So at 1 volt, we're going to have 1 amp, and at 2 volts, we're going to have 2. Similarly, volt, we're going to have 1, and at 2 volts, we're going to have 2. And that would be our IV characteristic right there. So this is I light minus I dark. It's very simple. So that is how you get the photocurrent of a piece of silicon using a lock-in amplifier. So sometimes what these systems do is they give you not I, but like the amplitude, the magnitude of I. So when you're giving a negative voltage, it's just going to be, so the photocurrent is more so going to look like this blue line. So just make sure that your system, check if your system is giving you the magnitude of I or the actual value of I. So it gets more complicated when we have non-ohmic contact. So whenever you don't have, like say when you have a shocky contact, what happens is your initial current is going to look more like an S-shaped, and we'll talk in a future video why that is. But so when that happens is you need to, becomes a bit more challenging, this step. This step with the lock-in amplifier becomes less so powerful, but it still works, but it becomes less so powerful. And we'll talk about that in the next video, and also the case for diodes. And similarly, shocky diodes. So thanks for watching. Hey guys, so I wanted to quickly include an actual measurement that I made. So this is N-type gallium arsenide, and we're actually measuring the magnitude of the photocurrent. So the y-axis is the magnitude of the photocurrent, but you can see that the photocurrent value is quite small, and that's what we expect. And the other thing that you notice is it's not perfectly linear or it's not perfectly symmetric between the left and the right side. So there are reasons as to why this is, and we'll talk about it in the future. So, but this is again the magnitude of the photocurrent, so it actually would look like this comparing to our earlier IV curve that we plotted. Yeah, so thanks.